Alright, for shits and giggles, I more or less have the same setup and the same transistor as the last video, the NPF 102, the third one I tested. And, yeah, I decided for shits and giggles I'd go ahead and try to test this thing as an amplifier. You can see I'm still, with my channel 2, I'm still measuring the current across that 100 ohm resistor. But, I'm measuring the voltage input, to the gate too with the other probe, channel 1. But otherwise, everything's identical, right? But I was like, while I'm at it, I might as well try to turn this thing into an amplifier. Um, so basically, I created a new scope here, and it's basically the same thing as before. I got the same kind of math channel trying to convert this, you know, channel 2 into a current waveform just so you can more see, because that's what this basic JFET is a voltage to current amplifier. And here you're seeing the effect. You can see that I got this, what my settings are here, and I got this set to 1 milliamp per division on the math channel there. And let me see if I can try to adjust the focus on this. I don't know if that's going to help really. I think it's just the screen's kind of washing it out. I don't know if that's better or not. But, and I created a new wave gen, and here is the gate control, and I'm generating a sine wave with these parameters into it. And again, it's kind of arbitrary, but it's functional, I'm just making sure that it's not positive as much as possible. If you can see the offsets and everything, the limits I tried setting on it. And I'm just using the other channel for DC, so I'm just applying across the drain. And going through that 100 ohm resistor, I'm just putting 5 volts across it, so I'm not doing anything with that. But so here's the waveform. In fact, I'm running this thing at 48 kilohertz. So and just to review you, that's my little function for that math channel. It's actually a stock function that you'll see in the examples. I just changed C1 to C2. So, but at any rate, but and set it to, of course, amps and so forth right there, just like I told you in a previous video. And then I set this to, 1 milliamp per division, so you can just, see the effect, because technically that's what this really is a current amplifier. I mean, in theory, you could feed this voltage, into like an op amp or something like that, right? And, and actually do something with it, or a microprocessor, so you can see the, if for some reason you wanted it in that form. I mean, normally you probably wouldn't use it this way, but, it shows it can be done. And, but yeah, you got a signal put there, and I can, change the type of signal, to like a square wave and a, ramp wave and, pulse, noise, sine power, and you'll notice that everything's in phase. So, our peak of our input corresponds to the peak across the current across the transistor, which also corresponds to the maximum current. And here's the minimum current, so troughs are aligned with troughs and peaks are aligned with peaks. So it's, it's a 100, it's not a 180 degree phase shift like you see in a lot of amplifiers. It's just a 0 degree phase shift. So it's kind of interesting to be able to do that, and just to show this operating as an amplifier without any kind of biasing or anything like that. I mean, this is the same test circuit I've been doing, and it shows that, that you can, actually kind of use this thing, and even if it's you're trying to test the parameters, you can use the same circuit, if you're careful, to test it as an amplifier too. So, we can see what happens as I increase the frequency. So you can see at some point here around about, these are times 1 probes too, but yeah, about 6 or so 100 kilohertz it starts to fall off, so again, part of that's the probes, part of that's the analog discovery, etc. But still, it's got a pretty good range, just as it is, up to about 500 or 600 kilohertz minimum. I'd have to look closely at what the 3 decibel point was. Remember, this analog discovery does have a built-in filter too, which can play tricks on you sometimes. Yeah, because they do. Because this analog discovery always samples at like 100 megasamples a second, but they do have some kind of built-in filter. I don't know if it's software or whatever, where it filters out higher range signals. So, and that varies. Most oscilloscopes, in fact, if you're interested in noise, analog discovery is an interesting case study in noise, because you can actually see the noise level increase as you set your bandwidth higher and higher and higher. On a signal, on your oscilloscope, you can literally see the noise floor increase and decrease. You can get it to less than 1 millivolt of noise. If you're, down into the 1 hertz or fractional hertz range, but it shoots up quite a bit. As you get, your your seconds per division, starts getting, smaller and smaller and smaller. Your bandwidth is increasing, so yeah, you can see the noise climb on it. Whereas a normal oscilloscope like this one, you don't actually see that. I mean, as it turned out, I probably should have made a video about that because it's kind of interesting. But the noise seemed consistent across every setting of the oscilloscope. But then again, the reason is the sampling rate changes, with every time you change your time base. Here it doesn't. I mean, the sampling rate's always 100 megabit, so, or megasample per second. So, but what they're doing is they have some kind of filter built into this thing. That's why it does an alias. If you see my aliasing videos, this thing does an alias, and it's because they have some kind of filter. I don't know if it's software or hardware, but they have some kind of filter in here that kind of tracks your setting. So it'll cut off higher frequencies proportional to where you set it, which means that it can distort your waveform. I can imagine like a 1 volt peak to peak, 60 hertz or let's say 10 hertz signal, with like a 1 megahertz, 0.1 volt signal riding on top of that. You probably couldn't see the 0.1 volt signal because it would probably filter that out because it's so high relative to the lowest frequency or the setting on your scope. So anyway, but yeah, so I mean, there's some properties that still takes some getting used to about this, learning your equipment, so to speak. But yeah, this operates as a pretty decent little amplifier just like this. So you can see plenty of noise, even though I got the noise envelope turned off. But again, part of that's probably because of my setup here too. But still, it's actually working pretty good for ever since I built that thing, I really haven't tested its frequency range. So it's working better than I would have expected, given how I rigged that thing up, in 20 minutes. Anyway, I just wanted to, demonstrate this being used as a crude amplifier with the same test setup that I was testing the family curves with. So, anyway, cheers.